Hello. 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 Is that coming through remotely? Is that coming through remotely? Hello. Is this okay? Hello. Okay, good. Hello. Is that coming through remotely? Is that coming through remotely? Hello. Is this okay? Hello. Okay, good. Hello. Is that coming through remotely? Is that coming through remotely? Hello. Is this okay? Hello.
Yes. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Welcome to the STEI ITB Quantum Day 2020 and 25. It is an honor to have all of you here for explore the fascinating world of quantum technology and its future implications. Today and February 2025, we gather to explore the fascinating world of quantum technology and its transformative potential for the future. This event, hosted by STEI ITB, brings together some of the brightest minds in academia, industry, and research to discuss the latest advancements and challenges in quantum computing, quantum communication, and beyond. Before we begin, I would like to extend warm welcome to our distinguished guests and our speakers today, Professor Rudney Van Meter from Kyoto University, Japan. Welcome to ITB. And from Anupam Mazumdar from University of Groningen, Netherlands, that will join in 3 p.m. And all of you as the audience for this event. Your presence here today is a testament to the growing interest and importance of quantum technology in shaping our future. Please give big round of applause for all of us and this event. Thank you very much. Now, let's move on to the first item on our agenda. That will be opening remarks from our dean that will delivered by Professor Adrian Suksmono. Please welcome in front of us to give a remark.
Distinguished guests, professors, colleagues, and students, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, and welcome to STEI Quantum Day, a special event in the celebration of the 19th anniversary of our school, STEI ITB, and the International Year of Quantum Science and Technology 2025. It is an honor to stand before you today as we gather to explore one of the most fascinating frontiers of science, quantum technology. This field, once confined to theoretical discussion, is now transforming industries, computing, and communication in ways we never imagined. As part of our commitment to advancing quantum research and education in CITB, we are privileged to have two distinguished speakers with us today. The first one is Professor Rodney Van Meter of Kyoto University, a leading expert in quantum networking and computing. He is also our adjunct professor in STEI. The second one is Professor Anupam Mazumdar, a renowned researcher in quantum physics, especially in macroscopic entanglement. He is a professor of Groningen University. Their insight will help us navigate the challenges and opportunities that lie ahead as we push the boundaries of quantum technology. STEI ITB has always been at the forefront of technological innovation in Indonesia. And as we celebrate our 19th year, we reaffirm our dedication to shaping the future of quantum science. This event is not just about knowledge sharing. It is a call to action for all of us, students, researchers, and industry leaders to collaborate and drive progress in this field. With that, I invite you all to engage into these discussions, ask questions, and be inspired. Let's make Stay Quantum Day 2025 a meaningful step toward a quantum-powered future. Thank you and enjoy the lectures. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Prof. Andrian, for your inspiring words and for setting the tone for today's event. Your support for quantum technology research and innovation is truly commendable. Now, let us move on to the highlight of today's event, our discussion session with two STEM experts in quantum technology. We will invite Professor Rodney to join me in the stage. Please give us applause for Professor Rodney. Have a seat. How are you today, Professor?
I'm fine, thank you. There we are. You should be able to hear me. Doesn't sound like it's on very loud, but I have a loud voice anyway. So thank you for having me. I'm very happy to be here.
Okay. For the first session, we have Professor Rodney, who will share his thought on network for modular quantum system. I will read his short CV. Professor Rodney von Meter received a BS in Engineering and Applied Science from the California Institute of Technology in 19. For the first session, we have Professor Rodney, who will share his thought on network. I'm sorry for the technical. Okay, I continue. And he got the PhD in computer science from ke-19 in 2006. And his current research centers on quantum computer architecture, quantum networking, and quantum education. He is the author of the book Quantum Networking. Other research interests include storage systems, networking, and post-Moore law computer architecture. Now he is a professor in environment and information studies in ke-19 Shonan Fujisawa campus. Okay, Professor Rodney, the floor is yours.
Thank you. So should I use this microphone or should I use that one?
I think it's Sam.
The same?
Yeah.
Okay. All right. So as you can see, we have a QR code up there if you would like to follow along with the slides. Those of you who have already opened it have probably seen that there are 170 slides there. So I hope you're strapped in and ready for a good afternoon. No, we're not going to talk about all of that. We're going to talk about a few of the things from it. And in fact, effectively, I think I'll have sort of two talks here. I'm going to spend about 20 minutes doing a very general introduction to us and our work and sort of the broad concepts of what we call the cyber informatics program at my university, at Keio University. And then we'll talk some about some of the technical work that my group has been doing in quantum computing, and this will be actually a really leading edge kind of topic. So, if you get lost in the second half, stick your hand up and we'll discuss it. All right. So the title that I've given you is Networks for Modular Quantum Systems, and I'll explain each of those topics as we go. As Professor Andrian mentioned in his introductory remarks, this is the International Year of Quantum, which is sponsored by UNESCO. And so this URL that you all can see up here, quantum2025.org, it gives you a connection to many of the events going on globally as we celebrate the International Year of Quantum. And why 2025? Why would that be the International Year of Quantum? Well, the earliest ideas in quantum mechanics began developing right around the year 1900, but the year 1925 is really considered an important year in the history of quantum mechanics. It saw, among other things, the publication of Paul Dirac's book titled Quantum Mechanics, the first real textbook on the topic, and also Schrödinger and Heisenberg and others published important papers in that year. So that brings us to today's event, which I wasn't actually anticipating that this would appear on such a globally prominent website. So I'm both very flattered and a little bit intimidated that this is on a UNESCO website. So I am, as introduced, I have a bunch of different titles. I'm involved in a great many different organizations. including being a board member of what's known as the WIDE project, which is ultimately the source of my connection to people here at ITB. And I'll show you a little bit more about that as we go. Note that the actual technical work that we're talking about here is not just work from me personally, but it's the work of a great group of people scattered across 6 or 8 different countries, and even within Japan, across about a half a dozen different institutions. And even this list is actually probably only a partial list. But this list is the set of people that I have worked with on quantum communications over the last 20 years, not even including the set of people that we're working with directly on quantum computing and quantum algorithms. So this is a picture of my research group starting or as of last fall. There are a total of, not everyone was in the picture, there are actually a total of about 40 people, ranging from project associate professors and project staff down to first-year undergraduates. So the young man in the front left there is, I think he is a second-year undergraduate. His name is Lars. And then to the right of me, we have students from India and Nepal, as well as other places. And so our group is actually very, very international these days. I think out of those 40 people, I think we have about 17 different passports. So it's quite a collaboration. Also within our community, we are the founders or creators of what's called the Quantum Internet Task Force, which is a group of people centered in Japan that we established. I wasn't sure if that was okay. That's all right. That's fine. It happens. We all do it. So the Quantum Internet Task Force we founded almost 6 years ago in May of 2019, involving 7 universities in Japan, 2 national laboratories, and 1 industry collaboration. The group there on the right is the group that was at that initial founding meeting. And I wasn't actually present at that meeting because it happened while I was actually in the United States for my sister's wedding. And sometimes you have to have priorities. Right? So let me tell you a little bit, actually, because I understand that this is a very general audience, that this is a very interdisciplinary audience. Let me ask, how many people here are actually, let's see, well, let's start from the other end. How many of you all are students? Good. How many of you are students in a technical area? Good. How many of you are in computer engineering or computer science or software engineering? Only a few. How many are in physics or applied physics or a related field? Everyone's embarrassed to say they're in physics. All right, that's okay, right? So what about like, for example, biomedical engineering? I know that there were some people from biomedical engineering. A couple, okay. So where are the rest of you all from? Are you from the School of Design or from? Oh, electrical engineering. Sorry, I didn't say electrical engineering. How many of you are actually in electrical engineering? Okay, good. That's the majority. All right. How many of you have actually studied quantum mechanics? Is that part of the curriculum here for electrical engineering? No, just Andrea, Professor Andrea, right? How many of you have had some introduction to quantum information or quantum computation or that level of things? Only a couple. Okay. Right. Well, so we're going to talk about some of these things as we go today. We'll give you sort of a very general overview of some of the key ideas, but my own personal background actually originally is in computer architecture and operating systems and storage systems and networks and things of that nature. I'm not originally a physicist or a quantum computing person myself. So for me, it's been a huge learning curve over the course of the last 20 years. I started working on quantum computing in 2003 when I was 37 years old, and I got my PhD in this when I was 40. So just about half of my career at this point is in the two different fields. So if you are going to work in quantum computing and work in quantum communications, you need to have a certain amount of background in physics, computer science, mathematics, maybe software engineering, maybe electrical engineering, maybe signal processing, maybe information theory. And nobody learns all of that in 4 years. Nobody really learns all of that in 10 years. And so really what we do is, up to this point, most of the work in quantum computing has taken place in very small groups, a handful of researchers working in one particular laboratory or one particular university. And then those people have had to sort of divide the problem up among themselves and work on specific areas. But the complexity of systems and the complexity of the entire environment, the set of problems you have to solve in order to build and deploy quantum technology, is so large that it's really no longer possible to do this in sort of one interdisciplinary, one group or one laboratory. You really need interdisciplinary collaborations across a great many different fields. So for example, all right, one more interactive question. How many of you all have heard of a little company called Google? Nobody's hands are going up, right? Google, no? All right. IBM, how many of you all have heard of IBM, right? So IBM, the Google and IBM are two of the most prominent companies working in quantum computing these days, and they're building their own systems. And I'm not sure of the exact number inside of Google, but I have heard that inside of IBM, their entire team that's working on quantum computing numbers more than 1,000 people at this point. So, and that's not, they don't have like 100 different projects or 100 different products. It's not that there are 10 people working on each one of these things. That's 1,000 people all pulling in one direction to build one system. So of course that represents a huge interdisciplinary effort. Everything from marketing and documentation and translation into multiple languages up through the electrical engineering and the software engineering and ultimately the physics involved in all of this. So, it's that's the kind of thing the kind of community that's required to do this. So before we get into sort of the details of the actual technical work that we're doing, I wanted to actually spend a few minutes telling you about my own view of the field of computing, and in particular, its relationship to society. And this, let me tell you about this from the point of view of what we call cyber informatics. So I'm a professor at Keio University, as was introduced. Keio has 6 different major campuses around the Tokyo area, and I am at the Shonan Fujisawa campus. At the Shonan Fujisawa campus, we have an undergraduate faculty that is called the Faculty of Environment and Information Studies, which I am part of. And then in the graduate school, we have a program that is known as the Cyber Informatics Program, and I am the chair of that Cyber Informatics Program. So if you look for the Cyber Informatics Program and Keio University, you'll find this essay or description of our program at the our research program and this particular program at the campus. So what is all of this? At our campus, of course, as I mentioned already, we do a lot of interdisciplinary work. There are many people throughout the world who are very pure technologists. And in particular in Japan, universities were set up such that they were very siloed, very vertically integrated. So most places you go and you study science and technology, you decide, when you're in high school at the age of 15 or 16, that's what you're going to work on, and you go straight up and straight through. But there's not really sort of a good set of lateral connections to how that technology actually impacts society. So at our campus was founded in the year 1990, and the goal of that campus is to of course, develop technology. I'm a pretty pure technologist, but it's even more about how to apply technology in the service of solving society's problems. And so that's what I discussed in this essay here that you can find online. And also, just as an example, there was a G7 summit in the year 2023 in Japan, and the prime minister was Prime Minister Kishida at the time. And one of the topics they talked about was generative AI, which I'm sure many of you are familiar with. I'm not going to put you on the spot and ask how many of the students have actually used generative AI in your homework assignments, right? But I'm sure your faculty are having direct and deep discussions on how to deal with the changes that generative AI is making in society, and that includes the process of teaching and the process of learning. I don't have a slide on it, but there was actually a thing that came out just in the last few days, some actual research that shows that people who depend too heavily on the use of AI in the learning process don't actually learn things as well. So that's the kind of study that needs to be done. That interaction between the effects of society, or the effect on society of technology. So 2 years ago at this G7 summit, one of the things that they noted was that it's very hard to stop forward progress on this. Excuse me, and that we need rules to balance the potential and the risk. And of course, the strategy is to create human-centric. That says rooms. That was supposed to say norms. I've been using this slide for almost 2 years, and I just now noticed that. I wonder if the spell checker did something to it just recently. So speaking of Hiroshima, this was a picture I took last year with a group of people in Hiroshima, actually very close to where that G7 summit was held. And the elderly gentleman right in the middle with the T-shirt that says "I am a force for science" is our professor Dave Farber. So Dave Farber is this was us traveling to Hiroshima for Dave's 90th birthday party. He is a professor in our group, at our university. And Dave is one of the people who helped to found the original ARPANET project that in the 1960s helped to create the foundation of what's called the internet today. Dave also, at a later point in life, was actually the chief scientist at the United States FCC, the Federal Communications Commission. So very much directly involved in how government policy affects science and technology as it goes. And the guy to the right of Dave in that picture, directly underneath the large lantern, is June Murai, who founded what's known as the WIDE Project. And June, in conjunction with that, the WIDE Project is the group of people who brought the internet to Japan in the 1990s. There were 3 groups of people that were working on internet-related technology in the 1990s in Japan. One was the WIDE Project, one was the national telecom carrier NTT, and one was a group of high-energy physicists known as the SciNet. So the SciNet people wanted internet technology for the use of scientists and technologists. We need this. This is a scientific tool. NTT wanted it for their internal business and internal development stuff. And the WIDE Project saw right away that the internet was going to change society as a whole. And so it was the internet for everyone was the driving principle right from the very beginning. And a little bit later, I have a couple of slides that I think will help show how that connects to where we are right here at IT Bunda. So Dave, let's see, I think I have one more slide on Dave here somewhere. Yes, so Dave is actually the head of what's known as the KO Cyber Civilization Research Center at this point. And so for those of you who are interested in this idea of how technology affects society, we have projects and seminars and various things going on with the Cyber Civilization Research Center that you can be involved in. Excuse me. There we go. That's a little better. So when I talk about cyber informatics, so one of the areas, one of the ways in which information technology can actually influence the world is this. This is a screenshot of a report on a particular earthquake that happened in Japan. I think this one was about a year ago. Oh no, it's already 2 years ago. You can see, so you can get this kind of information. So there are sensors out there that are connected that are measuring something in the real world, and then they're actually connected to the internet. And so you can use those to get information both about the past and also predictive information about the future, or warnings of currently happening earthquakes and tsunamis, which of course are familiar issues here in Indonesia. So I mentioned, the June Marai and the WIDE project. Many of the people on this stage are actually members of that WIDE project. And this is a group of us at what is known as IETF. IETF is the Internet Engineering Task Force, and that's the group of people that define the standards for the internet. So right now we are connected via Zoom across the internet. That means we are using the internet protocol and probably the TCP, which is the transport protocol. So it's a set of protocols known as TCP/IP. The IETF is the group of people who define that. The IETF meets 3 times a year in different places around the world, usually once in North America, once in Europe, and once in Asia. And the next upcoming meeting is next month in Bangkok. And within the IETF, there are many different working groups working on protocols for every aspect of the internet. There is also the IRTF, the Internet Research Task Force, and within the IRTF, we have the Quantum Internet Research Group, which I am chair of. So that gives you sort of an idea of this is involved in what we call governance of the internet, how you actually create the protocols and create the systems. And this is how those information systems actually create value for us in the real world. Let's shift directions just a little bit and talk about the relationship of quantum to the real world. In the year 2022, the Nobel Prize in Physics was given to Alain Aspect, John Clauser, and Anton Zeilinger for demonstrating that a concept known as quantum entanglement is actually real. It's a notion that arose in the 1930s when Einstein and others recognized a mathematical anomaly in the equations that govern quantum mechanics, and they said something very weird happens. For many years, it was thought that actually represented some sort of incompleteness in quantum mechanics itself. But then over the course of the last 40 years or so, a set of increasingly sophisticated experiments from these people as well as others have shown the reality of this quantum entanglement. We'll talk a little bit more about that later. And then finally, I think this is final almost, well, not quite, almost. Obviously, picture of the moon. This is a picture I took. This was during a total lunar eclipse that was a few years ago. And this is yet another example of how information technology interacts with the real or physical world. So I'm old. Well, I mean, not like 90 years old, but I'm old enough that when I was in high school, I had a telescope, and taking pictures of the moon involved film and a lot of hand control and development process. So you took pictures and then you sent the pictures away and you got back the film a week later. Okay. These days, all of that is done using digital technology, even by amateurs. And so the technology that's available is actually just astoundingly sophisticated and complex compared to what it was 40 or 50 years ago. So that's another place where this information actually shows up in the real world. Now, within this cyber informatics program that I am chair of, is I've given you sort of a almost a kaleidoscopic view of how information interacts in the real world and how it's actually governed and driven. We have a set of professors in our program who are involved in all of the different aspects of information technology, its development, its impact on society, and how it's governed and things of that nature. So those of you who are undergraduates who are potentially interested in graduate school in any of a wide variety of areas, we have a lot of different professors who are working on many different topics. So these are some of them, and these are some of the additional ones. But that brings me to a particular question. This cyber informatics program that we are talking about, one of the things that we need to think of or worry about is the question of what's a computer? What is a computer? Well, you might think of it as a box that takes in some numbers and it spits out some numbers. That's a very abstract notion of what the box is. And you might think that it's actually isolated from the physical environment. You might think, oh, well, I'm doing computational fluid dynamics, or I'm doing cryptography, or I'm doing something like that. And so it's just this thing that computes. But the reality is that these devices all connect to and interact with the real world. They're connecting to physical systems in the real world. So we can call that environment and information, or environmental information, and hence the name of our faculty, the Faculty of Environment and Information Studies. Excuse me. So the cyber informatics comes from the work of a guy named Norbert Wiener originally. I think he's the one who actually coined the term cybernetics. Norbert Wiener was a professor at MIT in the middle part of the 20th century, in the 1930s, 40s, 50s. And he coined this term cybernetics, which is essentially what today we might call control theory. So in Norbert's day, this was all about analog information. It was all about analog signals that you're actually measuring or working with. And so those signals come from physical sensors of some sort. And then you have some sort of system that actually processes those signals. And then you have an actuator that actually modifies the environment. And then you have this arrow that goes from right to left on this diagram that is feedback within the system. So what's important here is not just that you measure, calculate, actuate. It's this loop process and this control system that interacts in this iterative, connected way in this. Well, another issue. This is a woman named Margaret Hamilton, and she is standing next to printouts of a large pile of software code. She was in charge of the software code for this. Do any of you all know what this is? Apollo 11. We've got some very knowledgeable people here in the front row. That was Apollo 11. The first manned mission or crewed mission that went to the moon. It was manned because there were only men on it at that time. And it was actually seen by people all around the world, I'm certain including many people here in Indonesia. This is a frame I grabbed from a video that's available on the web, which shows people in Japan actually watching it. Now, another issue. This is a radio telescope, and once again, this is a group of people that are part of the WIDE project. And you might think that what this is one single radio telescope, but in fact, this set of dishes that are in this picture, these are not 2 or 3 different radio telescopes. The 3 radio telescopes here, or 3 dishes that you see here, collectively make one telescope. This is one instrument. In order to do this, they use a process that's known as interferometry, in Japanese kanshoke. And this is at a place up in the Japanese Alps called Nobayama. Well, this idea of interferometry can be used not just between a set of dishes that are 100 meters apart or something, but this is a woman named Katie Bowman, who's now a professor at Caltech. And this photo captures her delight at the moment that she first saw that picture that's on her laptop, which is this, which is the first picture we have actually managed to take of a black hole. This is the black hole at the center of the M87 galaxy, which is 55 million light years away. This picture is about 1,500 light years across, and the black hole is about 1 light year across. So everything in this picture is smaller than one picture in the middle, 1 pixel in the middle of this picture. And this was created using this technique of interferometry across the entire globe. They used a set of antennas that were spread across thousands of kilometers and collected data for days using this as the Earth rotated, and then correlated all of the signals to create this one fabulous picture. So once again, we're applying technology in the real world. Katie is a professor of computer science. She writes code. She and her team write digital code for processing digital data. But it interacts with what's going on in the real world. So again, this is that idea of information actually interacting with the outside world. And in particular, this technique is called very long baseline interferometry, or in Japanese, chocho kisen denpa kanshoho. I have no idea what you call it in Bahasa Indonesian. Any idea what do you call it in Indonesian? Do you know? No. All right. Let's see. Let's skip that and move on. This was when the result was actually announced. So that we've talked about the cyber informatics techniques. We've talked about we're talking about cybernetics, Norbert Wiener's cybernetics. We've talked about this interferometry at the digital level and at the analog level. This is a paper that was proposed about 10 years ago now, more than 10 years ago. This was 2011, that proposed that you could do the same thing using individual photons, using the techniques of quantum computing, quantum information in the real world, to do something that would improve the resolution, potentially even beyond what that photo of the black hole shows. It would give you better angular resolution. Now, the challenge is whether or not we can actually build that. It's going to be extremely difficult. It's going to be just an extraordinarily difficult thing to achieve. All right. This brings us to sort of a summary of that entire set of topics. Let's see if we can put some structure on that. Over the course of the last century, 100 years ago, even movies, cinemas, and recorded music or recorded voice, they were still relatively new technologies. Those are an analog form of information, shown, as you can see, in the upper right up there. In the middle part of the 20th century, and then particularly in the second half of the 20th century, we started to shift from analog information to digital information. That digital information gives us a lot of advantages. It gives us better ability to actually process the information. It gives us better ability to protect the information using error correction, whereas analog signals tend to degrade over time. And now we stand right here at the year 2025. We are in the midst of the transition. Well, it's really still just at the start of the transition from digital information to quantum information. Now, even within that, that doesn't mean that analog information goes away, and it doesn't mean that digital information goes away. It just means that there's this third paradigm. We have quantum information as a third paradigm. All right. When I teach quantum information processing to undergraduates, I have a course, the course we call Quantum Information Processing, which is intended to be accessible even to first-year undergraduate students. Within that, I try to teach 7 basic concepts. Those 7 concepts are superposition, interference, entanglement, unitary or reversible evolution, measurement, decoherence, and the no cloning theorem. If you can understand those 7 concepts, and we're not going to go into them today, but if you can understand those 7 concepts, then you understand enough to know a great deal about how quantum computing actually works. Which brings us to this glorious device. This glorious device is a machine built by a little company called IBM, which exists in a city in Japan named Kawasaki, and the machine itself is also named Kawasaki. IBM currently names all of their quantum computers after the names of cities. This is the only one that's actually in the city it's named for. The rest of them are named for San Francisco and Tokyo and Jakarta and Rio and Lima and all these places, and none of them actually exist in those actual places. So in order to study this quantum computing, there are a few technical topics you do need to sort of learn. One of them is the basics of linear algebra, meaning matrices and vectors and eigenvectors and things like that. The basics of discrete probability, what happens when you roll a set of dice or something. And then the basics of some sort of programming language. Python is certainly good. With that, you can actually program these real quantum computers. And so if you come to our campus, you can come join my research group and actually use those IBM machines. Following on from that, 2 years ago, I taught a brand new class called Quantum Internet in English, and this again is for undergraduates. And I believe that this is the first course on quantum internet communications for undergraduates anywhere in the world. All right. And that brings us back to this notion of quantum entanglement that I talked about earlier. In quantum entanglement, you have 2 variables, what we call qubits usually, and they share a state. They are random, but not independent. And this is not the same thing as classical correlated probabilities. This is not the same thing as dependent probabilities in classical probability theory. What it is literally a single shared state. And with that state, you can compute and you can communicate and you can create these interference patterns and things like that I was talking about earlier. With that, there are actually 2 tracks in the development of quantum communications. The upper track that's shown there is quantum key distribution, which uses single photons, but generally speaking, doesn't use this full entanglement that I was talking about. That bottom track is the development of entangled networks, and that's actually the area where we're actually doing most of our own research. And this brings us back again to these 3 gentlemen and their collaborators who have done such fantastic experimental work over the last half century, showing the reality of quantum entanglement. So 20, 30, 40, 50 years ago, demonstrating that in the laboratory was extraordinarily difficult. It was Nobel Prize worthy work. These days, you can buy a kit that will do it. Or you can build your own, and we have been building our own. All right. One more little detour here, and then we're going to get into the actual technical stuff. This is a diagram of a set of wrens. Who here knows what a wren is? Anybody know what a wren is? Nobody? Nobody in the whole room knows what a wren is. A wren is a research and education network. So the internet is not one network. That inter in internet, that means between. The internet is actually a global network that is composed of about 70 or 80,000 other networks. So there are 70 or 80,000 organizations that each run a network, and they all connect and cooperate together to form this global internet that we have. Within that set of 70 or 80,000 networks, a subset of those are what we call RENs. They are research and education networks run by researchers and educators for the purpose of doing research and education. This is a map of some of the ones in this part of the world. Notice that right there near the middle bottom where it says ID, that comes to Malang. That comes to Brawijaya, which I gather is not close to here, right? It's still a little bit of a ways from here. We would love to see that network actually extended from Brawijaya over to here. It's something to talk about in the long run. This slide says Arena Pack. This Arena Pack is actually a REN that's actually run by the WIDE project and others. I'll show you a little bit more about that in a second. There's the Arena Pack website. This beautiful photo. I'm not sure if that's actually one of the undersea cables that carries our data or not, but it's operated by the WIDE project. And portions of this particular map is not designed to show you specifically which cables are the Arena Pack, but basically the group of cables that originate at Guam and radiate out from there are the Arena Pack. So if you want to get involved in that sort of thing, you can join a program that's known as API, the Asia Pacific Internet Engineering Program, which is an education and operations, network operations program operated by the WIDE project for people in the ASEAN area and throughout Southeast Asia and connecting to other places as well. If you do that, there are a set of courses and a set of things you can be involved in. The first couple are online. The first two modules, understanding the internet and then operating the internet, are things that you just online courses that you take and learn from. After you have passed those two things, then you can join what's called the API Camp. And the API Camp is a face-to-face camp, 5 days of hands-on work that's actually building out a network and actually operating network routers and servers. The very first one of those API camps was actually held right here on this campus, run by, let's see, do I have who's this photo in here or not? Let's see. So this is a picture from 2 years ago. Just to my right in the blue shirt, of course, the farthest to the right, you see Professor Suksmono. And between him and me, that's Husni Tamrin, who is a graduate of ITB for his undergraduate and then did his PhD with us in Japan. And he actually operates and does a bunch of this stuff. So if you're interested in network operations, this is a great chance and a great way to be involved. So this was about 1.5 years ago, a little under 2 years ago, that I was here for a visit. And on that occasion, we actually did do an entire lecture driving straight off of the whiteboard, actually, of those same set of 7 concepts. This photo was taken when there were still 6 on the board. But those 7 concepts that I mentioned earlier. So 7 principles, but this actually shows you the steps in the algorithm, how that actually goes. So we can do that one again sometime. Maybe on my next visit, we'll go do a basic run through of quantum algorithms and whatnot again. Yes, number 6 was celebrate. That's when the algorithm actually works. So this is, even though the title up there says 7 principles of information, the 7 principles of information were already erased from the board at this point, and this is how the algorithm itself actually works. That's assuming your computation actually works. If your computation doesn't work, then no celebration. Okay. All right. Let's see. That's probably a reasonable summary of, over the course of this, going all the way back, the overall issue of cyber informatics and how information operates in the real world, including in human society and including at our campus, and what's going on with that. Let me take a pause here and ask if people have questions about this, about these 3 paradigms: analog, digital, and quantum, as well as about the issues around network operations and the learning process and the interaction between the WIDE project and the Soy Asia project and the API project and things like that. Let me ask, are there questions? Better yet, whenever I say, are there questions, people, the room's always quiet, but I know there are questions, right? So let's say it this way. What questions do you have? I will now pause until someone actually asks a question.
Is there any question? I think there's no questions.
I don't believe you. I am certain there are questions. So when I teach my own undergraduate classes, when nobody has a question, I actually point to somebody and say, "What question do you have?" Right? All right.
Okay.
Maybe just a small thing. I think you showed one diagram when you mentioned about cybernetics. You showed us a PID,
Yeah.
PID control diagram. It's very.
This one.
I use this for my slides. Yeah, I plagiarized this. This is favorite favorite picture. But what is this related to quantum things?
So this is a general notion in information systems, of course, and this was originally developed in the context of analog systems, but so this is a very general notion for how you can do something like even create a governor that controls how fast a motor works. But if you want to ask specifically how these notions actually connect to quantum information, people who understand this can work on the control of the quantum computer systems themselves. So the individual qubits inside a quantum computer actually are controlled via analog devices. One of those devices in particular is a thing called an AWG, an arbitrary waveform generator. And so the programming of that AWG, including the sensing of signals that come out of the device and recalculating something and then giving it back as control, all of that control loop process is actually critical to the operation of quantum computers. And in fact, it's not my own specialty, but one of our other professors is actually a specialist in this particular area. He started out with classical control theory and then shifted into actually applying it to quantum computing systems. So yeah, sure. What's the meaning of quantum internet? Ooh, that's a good question. The meaning of quantum internet to me, at least, yeah, let's see, where did the roadmap go? Is the quantum internet is a system for distributing entanglement globally. Okay. this notion of quantum entanglement, these shared states that are shared between over a distance. They can be used to move data around, to create highly sophisticated sensors, and they can be used to do digital quantum computation over a distributed area. So the job of the quantum internet then is to make and distribute that entanglement so that it can be used by those other devices and those other applications. So I will point out, I don't have a slide on that in this particular slide set, although I do in some of my other slide sets. About 17 or 18 years ago, there was a researcher named Jeff Kimball, who was a professor at Caltech, but I didn't know him personally. He came to Caltech after I graduated. Jeff wrote an article that was published in Nature that was just called "The Quantum Internet." But Jeff is a physicist. Jeff is not a network engineer. Jeff wrote an article with the title "The Quantum Internet," and the only thing it talked about was how to make entanglement using some particular physical mechanism over some distance, which is not the same thing as doing network engineering. That doesn't. About 2010, so it's about 15 years ago. And sadly, Jeff actually died last fall of cancer. I think he was around 70. He wasn't very old. So that article really annoyed me because it had quantum internet in the title, and it didn't even really tell you anything about one network, let alone internetworking as we internet engineers actually think of it. So, the title and the content didn't seem to match to me. So it really annoyed me. But the content itself is actually fine and important. Other questions? We should get one from a student here. Oh, okay. We got one more faculty question, then we'll get one from a student.
Okay, I am one of the old guys who were worried about this because I know nothing about quantum and I'm afraid of studying quantum physics. How do I learn or unlearn my classical physics before I learn quantum physics? Is there? I'm very, very afraid in going into this direction because I thought, this is going to be very, very difficult for me because I have so many baggage in my head, kind of.
So that's a good question, and the issue is not that quantum computing is actually hard. Quantum computing is not actually that hard. What it is weird and unexpected and not like anything else we've ever done. So if you invested as much time in studying quantum stuff as you have already invested in studying classical stuff, then the reverse would be true. Classical information would seem very weird and strange and limiting. But of course, we don't live in the quantum world. We live in the classical world. And so the classical world translates much more easily to things that are familiar to us in the real world. But the underlying mathematics and the underlying concepts in quantum stuff, they're often counterintuitive and in some cases even wild. But once you get used to those basic concepts, they're not as hard as it seems initially. And if you want to actually learn this stuff, actually, we have where I think the slide is all the way at the end of this. We actually have an online course that we created now about 7 or 8 years ago. That I believe is actually still free. And we created it initially in English. It was the first course that KO actually created online in English on this platform known as FutureLearn. And with the support of Husni and some of the people right here at ITB, including Professor Andrian, let's see, I've forgotten who else was involved in that. Who else was involved in that? You were involved in that, right? They translated the materials for this into Bahasa Indonesia. And so it originated in English, but it's also available in Japanese, Thai, and Indonesian. So one of the four most important languages in the world, right? So you want to learn this? This is about 20 hours worth of material on in a set of video lectures, as well as a set of written articles and some little online JavaScript apps that you can play with that demonstrate some of the concepts. So you can get that from there. I see a couple of people with their phones up, so I'll leave that up for just a little bit longer. For those of you who came in late, by the way, a bunch of you all came in. I guess you have probably had some other meeting or something, or class or something beforehand. If you want to get the slides, you can pick up these the slides from here. There are many, many, many slides in this slide set. The people grabbing their phones, I see. Good. That's what they're there for. And feel free to share that around with your friends and fellow students. All right. This gets us, about 20% of the way through my set of slides, doesn't it? And we need to finish up by 2:30? By 2:30. All right. So let me talk a little bit actually now about some of the hardcore technical stuff, which will be, I think, some of the give you an idea of where the leading edge in research actually is. And this is the part that's actually most directly relevant to the actual title I gave of modular computer systems. Modular networks for modular quantum systems. This, rather obviously, is not a quantum computer. This is the world's fastest classical supercomputer, currently at Lawrence Livermore National Laboratories, the El Capitan system. And I want to connect it to this, which is one of the world's most advanced quantum networks, which is the one in our laboratory. So there's a little bit of a gap between this and this, right? Just a little. Right? So first off, let me give you a very, very rough look at the necessary roadmap we need to follow for the evolution of the technology over the coming decades. So in the early days, already now close to 30 years ago, we had early systems that had qubits in them. But of course, we wanted to have more application qubits. A qubit is a quantum bit, and we wanted to have more of them so that we could solve larger problems. But we also needed those to be higher quality or higher fidelity as we developed. So we started out in the lower left-hand corner, and we want to get to the upper right-hand corners of the place. Well, we entered the era, about 6 or 7 years ago, of what is called NISQ, Noisy Intermediate Scale Quantum Systems, which is a term that was coined by Professor John Preskill from Caltech again. And then we have moved over the last couple of years toward systems that are bigger but still have a lot of noise, to some that are smaller but have a little less noise. And then for the first demonstrations of what's known as quantum error correction or quantum fault tolerance. So those first devices really exist today. So this is pretty much where we are today. But eventually, we want to increase our ability to actually do error correction in the systems, and so that's what we call longer code distances. And then eventually we will get to the point where we have as many of these qubits in one chip or one device as can actually fit in that technology. I call that MaxSQ, the maximum single chip quantum system. That might be just a few logical quantum bits, because in fact, the physical devices for this are many orders of magnitude larger than classical transistors. And so the number of devices you can fit into one chip is much smaller. Once you hit that limit, then eventually we want to add interconnects to these systems and connect multiple of these devices together into larger systems. That's what our research as a group is actually working on. That's the networks for modular quantum computing systems that we are building and working with. Now, some years ago, I published a paper in IEEE Computer called The Path to Scalable Distributed Quantum Computing. Right? More recently, we've been involved in what we call system area networks or multi-computer quantum interconnects. Both of these you can find on the web if you look for them. But the earliest publication that I can find and that I recall from this, these ideas were first published by Professor Jungsang Kim, who is now at Duke University. Well, actually, he was already at Duke by the time he published this stuff. So in the time frame of 2005 to 2009, he was trying to design systems that would do this. Now you can see the bottom part of the image there on the right. The green boxes are detectors for single photons using a special technique called Bell state analysis. And that's why it says Bell detectors there. On the left-hand side of that image are these little gray boxes that are essentially sets of quantum computers. They're a set of quantum computers. In between is this purple box, that just says N by N optical cross connect. That's the box that we're working on. This idea was proposed 20 years ago, and nobody has built one yet. But in my own PhD thesis, all the way back in 2006, I actually analyzed these kinds of systems, starting from the high level of the system, going down to the lower level of the system. So working from the notion of what do we want a computer system to be? Not what's technologically possible, but what do we want the system to actually be? Geez, that means I'm old because this was 2006. And I was already 40 when I got my PhD, so I'm a lot older now. So in order to do this, in order to go through this design process, we have a whole set of questions that we need to address. We need to go through, how many of these physical qubits can you fit in one of these nodes in your system? How are you going to make this entanglement between the nodes? How do you do quantum error correction? How do you do logical operations between the nodes? What's the switching technology? What's the network topology? How are you going to lay all of this out? And in particular, what's the traffic pattern? And I want to show you a little bit about that first, just so you get an idea of what the design process is like. And then maybe we'll stop there and we'll open it back up for some discussion after we go through just a little bit of this. All right, so if you have a set of quantum computers and you want to use this set of quantum computers to solve one problem that's bigger or harder than you can actually solve using just one of those computers, then you need to communicate between them. That needs to be done using this quantum entanglement. It needs to be done in this quantum fashion. So we've got a set of 4 quantum computers here. We've got a cloud in the middle that connects them. And let's say that in our first round of communication, we want to move things around sort of the perimeter of this square. But then in a later round of communication, we might want to actually send information crosswise across the diagonals of this. Excuse me. And then perhaps in the third round, we go back to this kind of circular loop of communication. So this is the traffic pattern. This tells us what the needs are based on what the algorithm is that you're running. This is not dependent on the hardware. This is a requirement for what the hardware needs to be able to do. This drives our design process, knowing what that interaction actually is. Now, I'm not going to go into the details of this kind of interaction, but these are the kinds of technical diagrams we use for actually analyzing this. And the red and blue lines there actually represent 2 different ways at the logical level of splitting up the computation among the set of nodes in this. And that will change this traffic pattern. Now, let me skip this part a little bit in the interests of time here. and show you. So these are some other ideas that other people have actually worked on over the years. But I actually want to talk about the actual network topology that connects all of these things together, because that's the thing we've been working on hardest for the last 6 months. Now, if you wanted to connect these nodes to another set of nodes, you might start with one quantum computer, and you might want to connect that out in 4 directions. Canonically, we'll call those north, east, south, and west. Then when you scale the system up, it starts to look something like this. Okay. That's nice. That's actually kind of like some of the earliest really large scale supercomputers were done in the 1980s and 90s. In the case of quantum systems, though, it actually means that each one of those links actually requires an additional device in the middle of the link that is called a Bell state analyzer. That Bell state analyzer looks something like this. So that means every place where you have this line connecting 2 nodes together, you need to put one of these in the middle of it. That's not very efficient in terms of constructing your system. So what we do, this is equivalent to this one device here in the middle of this. But in fact, that black cylinder actually contains a bunch of these detectors. So it's not just like one of these devices, it's like a set of these devices. So that tells us that in fact, what we would like to do is we would like to put the nodes on the left and that set of detectors on the right and run it through some sort of network in the middle. So that diagram that I showed that Jung-Sang Kim was talking about in 2005 is actually really pretty much the right direction. Now, what you might do, you might want to connect, the top computer and the bottom computer there. What they do is they each emit a single photon, and those single photons have to fly through this network and come together at this Bell state analyzer. The 2 photons must match. They must meet at that point in time and space. So you could do this with a good network. You could actually have multiple connections running at the same time. They have both the blue one and the red one there. Let's see. Let me skip that and show you some of this. Walk through some of this. Because I want to show you actually some of the experimental work we're doing. All right, so that carries us all the way through to this classical supercomputer again. That classical supercomputer uses an approach known as the Dragonfly network. I didn't say dragon, I said dragonfly, right? It sounds like we've got a dragon in the room though, right? So this notion of a classical dragonfly network, what we do is we divide the set of nodes up into a set of groups. And another drawing of the same kind of thing would be something like this, where within each group, all of the nodes are connected to each other, and then the groups are actually connected to each other. We want to do the same thing for quantum systems, where we have a switch. So in the bottom part of this diagram are the quantum computers. On the right-hand side are those Bell state analyzers. And in the middle is that switch with some of the links dedicated to actually connecting those nodes together and some of them dedicated to connecting to other groups. The BSA is the Bell state analyzer. Yeah, so that's the thing that helps us create entanglement between the 2 nodes. Is that commentary on my presentation here? I'm not sure. All right. So the final question then is, can we do this? And we actually have a laboratory where we were working on doing this, and this is some of the experimental work going on. And that ultimately draws us to a network that looks something like this. The part in pink is the part we have actually developed, and the rest of it is still for future work. But as you scale it up, it would look something like this, and you would have connections that look like that, or connections that look like that, or connections that look like that as you use the network. And so this work is actually available on the, there's a preprint of this that's available. You can pick that up from the internet. And that brings us to some final comments. if you are interested in these issues of quantum communications, we have a Creative Commons licensed quantum communication textbook that we have written that we are in the process of getting published. And this course that I mentioned a little while ago, and I think that's about it. So this woman is Monet Tokuyama, who's a member of my group. And if you want to actually get a copy of her bachelor's thesis, that URL will take you to that. It's 165 pages describing how to construct a particular type of quantum node known as an ion trap. And I think that's it. So thank you all for your attention across this rather long-ranging and kaleidoscopic journey.
Yeah, thank you very much, Professor Rutne, for your very insightful presentation. Now we will move on into the question and answer session for this session. If anyone in the audience here have any question, please raise your hand. Or the audience in Zoom meeting.
Yeah, we have a question here.
Okay.
There's a third mic here. Do you want to? Please do that. I'm going to take this over.
Okay.
Say hi.
Hi.
All right.
My name is Sami, Professor. I am currently an electrical engineer, undergraduate.
Good.
Can
We
I
need
ask,
electrical engineers.
can I ask about the quantum computer specifically? About the applications.
About applications for quantum.
Yeah. So I just want to know. I have seen in one game that quantum computer is so fast. Is it in the real world? It will be like you can play maybe a game like more with more sophisticated graphics or whatever is that. But in one game that I saw is you can like have a database or something like that, but the computer doesn't have to like organize it. It is because the maybe the quantum processing or whatever is that is it's so fast, so we can just search it like for a specific file or folder, and in uh, in just milliseconds or in a short time we can get it so fast. So if we compare it to computers nowadays, if we search a file from maybe I want to search a specific file with a name, with a specific name, and I search it in like in C drive, it takes so long time.
Yeah.
Okay. Yeah, but is it possible for quantum computer like to search it and then just take just a couple of milliseconds like that, or?
So that's a very good question. So thank you for asking. I debated when putting this talk together about how much to actually talk about what quantum computers are capable of, as opposed to talking about the technical work we've actually been doing. It's really important to understand that quantum computers aren't fast. In fact, they're really, really slow. So then what's the value? What's the point? Why are we building these things? Well, the answer is that quantum computers have a different computational complexity than classical computers. Now, what does that mean? What what computational complexity means is that as your problem gets bigger, every problem gets harder to solve. Right? The question is, when the problem gets bigger, how much harder does it get to solve? So, excuse me. For example, if you're looking to decrypt some data, you want to decrypt somebody's message, you need to find the key that they actually used to encrypt that message. Every time they add one bit to that key, that means there are twice as many possible numbers that could be the key. And so you have twice as many things to search for. So that growth is what you would say is exponential. As you add one, every time you add one bit to it, the problem gets twice as hard. Now, quantum computers, we would hope will be able to solve some problems without paying that exponential cost. Decrypting data directly is not one of those, but there's a related problem known as factoring a large integer that's actually related to how we generate those keys that we use for encryption. And quantum computers are believed to be able to solve those problems in time complexity that's polynomial in the length of the key rather than exponential in the length of that key. And so solving the problem for 10 bits or 100 bits, a quantum computer is going to be way slower than a classical computer. But solving it for 1,000 bits, it will be way faster than a classical computer. So it's that difference in the computational complexity that we're looking for with quantum computers. In our online course, one of the things one of the examples we walk through is games like chess or shogi or checkers or Go or Weiqi or Baduk. Each of those has a relatively small state space or relatively small state description. It only takes you a few bytes to describe where all of the pieces are on a chessboard. But figuring out what all of the possible sets of moves are over the next 10 or 20 or 30 moves in a chess game is exponentially hard because you have 5 choices the first time, then you have 8 choices the second time, and you have 11 choices the third time, and multiplying each of those out, you get this exponential growth in how many possible game trees there are. Quantum computers, we think, will be able to search spaces like that much more efficiently than classical computers can. And so what quantum computers do is they don't make everything faster. What they do is change the set of problems that it is practical to look for solutions for. Now, what are the kinds of things we can use that for? Optimization is one area. You're being able to solve like logistics optimization problems and things like that. Another area is computational chemistry, which is which was actually the original proposal for quantum computers. They were proposed to be useful for solving problems in quantum chemistry. And that means it has impact on things like material science and drug design and industrial chemical processes and things like that. If we can use quantum computers to solve even just a few of those really important problems, then quantum computers will be worth all of the investment that we are making in time and energy and people's effort and things like that, because those problems are very hard and they are potentially very valuable to society. How are we doing time-wise? Do we have time for one or two more? It's already 29
We
now.
still have
Thank you for the answer, Professor.
You're welcome.
We still
Do we have time for
Yes.
okay?
Is there any
Yeah.
questions?
We have a couple more here.
So what I want to ask is rather a simple question or maybe a basic question for you, but I'm really curious about the quantum language, because as you mentioned before, analog is a continuous signal, but in digital it's a bunch of 0 and 1. But in a quantum computing, you are using qubits. So what exactly is qubits? All I know is, from what I know, qubits is a number between 0 and 1, but it's collapse. I don't know. I don't really get it. Like Mr. Kahakjo mentioned before, quantum world is rather terrifying for me to learn. Like, it's weird. You can quantum tunneling, like what? I don't know.
It kind of makes the hair stand up on the back of your neck, doesn't it? It's just completely different. It's like, ooh, that's kind of weird. But that's okay. That's part of what makes it interesting. As to your specific question, how you actually program these things, one of the most widely used tools in the world is actually developed by IBM, and it's a software toolkit called Qiskit, which exists in Python. And so all in terms of writing the code, all you have to do is be able to work in Python to be able to program a quantum computer. But the way you are expressing an algorithm in that language is via what are known as quantum gates. And those quantum gates are the quantum equivalent of and or and not and XOR. So it's a very low level approach to actually doing the programming of the systems. So you have to have a in your head a notion of how the algorithm is going to work, and then you have to figure out how to translate that into a set of gates. So that means that we are basically at the same level with programming languages for quantum systems that we were at for classical systems in the 1950s and 60s. There is a huge amount of work to be done on designing intuitive programming languages, easy to use programming languages that are very expressive in terms of these quantum interference patterns you want to generate. That whole area of designing programming languages for quantum computers is a research field in its own right. If you want to work on that, come join my research group. We have been doing work on related topics off and on for 10 or 15 years. And about 8 or 9 years ago, I was at a workshop in Europe that was a workshop on quantum programming languages. And there were about 60 people there. And that was one person each from a bunch of different research groups. So even, 7 or 8 or 9 years ago, there were 60 or more research groups around the world who were working on quantum programming languages, and that's not enough. There are not nearly enough people working on this problem. It's incredibly important, and it's not getting as much attention as it needs. How are we doing time-wise?
Maybe one more question.
Okay.
Is there any other questions? Okay. Okay. Please,
one of
for
the women,
female student.
One of the women students or faculty have any questions? No.
Maybe from the Zoom meeting. Is there any questions? One female. You can point one on.
You want me to point to somebody?
Female only.
I'll do that. All right. What about you?
Me?
Yes. What questions do you have? You've been sitting here listening to me talk for an hour and a half, right?
Don't get it. What is computing? Quantum computing. I'm interested from the question from Mr. about quantum internet, but yeah, is it possible in how to say urban or district to have quantum computing, because there are a limited of how to say accommodating or facilitate from the internet not working?
So actually, that's a question that we're actually studying right now in the Tokyo area, is how to get access to the optical fibers that we need in order to actually build a Tokyo area quantum network test bed. Interestingly, in Japan, one of the groups of people who actually own the most fiber that's not actually being used is actually the railroad companies. They have fiber that is strung along their rail lines that they use for their own communications, but they actually also have a lot of spare channels, a lot of spare fibers that we'd actually be able to use. So that's I talked a little bit about the research and education networks for classical systems. We need to worry about it for quantum systems as well. And so those levels of governance, somebody needs to take on the task of managing that level of things as we go forward too. So we need a complete ecosystem of people. Which brings me actually to, I guess, my last comment. I was posting on Facebook about being here today last night, and one of my friends who's actually from Nepal actually said, hey, you should talk about how developing countries can benefit from quantum computing and how we can get some advantage there. And my immediate thought was, yeah, that's important. But for me, as an educator and researcher, I'm actually interested in the flip side of that. How can we get people from developing countries to participate in the research and development that's driving these systems, so that it's not all just driven by one handful of white American men in Silicon Valley. Right? This needs to be a global effort because it needs to benefit people throughout the world, and not just to be something that makes a handful of rich people richer.
Thank you very much. Any other questions again? Okay, the last one, I think.
Last one here. Then.
Yes.
Do we have a mic?
Please give the mic.
You mentioned that quantum computer can decrypt encrypted data better than classical computer. How to design cryptographic algorithm to secure our existing data from quantum computer decryption? What checklist and criteria we should do to design the algorithm?
That's that interaction of society and technology again, isn't it? Because actually, although factoring numbers and potentially impacting classical encryption was one of the things that got people excited about quantum computers in the first place. It's actually kind of an antisocial application, isn't it? Let's break everybody's encryption. That's not really a great reason to build computer systems to ruin everybody's lives, right? But in the classical community, there's an entire community of people who are creating what's known as PQC, post-quantum cryptography. So if you search the internet for that, look for PQC. There are research groups around the world who have been doing that, who have been working on that problem for more than a decade. And in fact, the U.S. National Institute of Standards and Technology, or NIST, has been running a competition for about 6 or 7 years now to find a new standard to replace the existing classical encryption mechanisms that are potentially vulnerable to quantum computation. And so that whole PQC thing is out there. People are developing it. And I just saw in the news actually a couple of days ago that China has decided to develop their own PQC algorithms out of concern that anything that comes out of the United States might potentially have a backdoor in it or some weakness in it that would allow the U.S. NSA to break things more easily. And so the Chinese want to have their own standard, which is developed independently of what's actually being developed in the United States. I think it's actually a noble goal to have a system that's widely analyzed and widely understood by people throughout the world. And the way you do that is by actually publishing standards in the open and publishing analysis of things in the open. But it doesn't completely alleviate people's concerns in the case of classical cryptography. And so that's actually a valid concern. I think in the end there will be competing standards on it.
Thank you.
Okay, thank you very much for the question. And then I think this is the end for the first session for Prof. Rooney. Thank you very much for your insightful presentation. Please again give a round of applause for Prof. Rooney.
Thank you all for your attention and for the great questions.
Okay. Now we will move on for the before we conclude this session, we will be express our gratitude to our Prof. Rooney presentation as speaker today for their invaluable contribution. As a token of appreciation, we will now present a special gift from us for you that will be delivered from Professor Anjan Suksmono. We have in front of him. This is the special thank for Professor Rodney. Balik, Pak. Maybe one picture from the other side. Okay, Prof. Rene and Prof. Lester, yes. You will be well seated. Okay, more expressive, maybe with stay like this or 1, 2, 3. Okay, thank you very much. Okay, we'll continue again for the second lecture from Groningen University, Mr. Professor Anupam Muzandar in 3 p.m. So we will have a coffee break for 10 minutes. You can get out of the door and then go back again here for 3 p.m. Okay. Please have a breakfast, coffee break, I mean.
This one, I was given this critique when I was here in 2023. And you all gave me this. You will appreciate it. My wife is very patient with the fact that I travel so much. So nice to be able to take something back. Sure. Well, let's join the students. Hopefully, in fact, often when I go places, one of the things
Let's be honest for a second.
already. Already.
Being over your head. There's no
My watermelon. Somebody else to have to drink my watermelon. That's fine.
Yeah.
What do you think? Anything?
I like that I have many.
Don't we all? Don't we all? I don't know anything about your field, right? You can teach me.
But I don't want to see this like everything like that, right? How do I do that? Because
Same way as anybody.
the undergrad one. So I just follow the translated course, right?
Because that will get you, that 20 hours will get you enough of an idea of what the ideas are and why you should be thinking about it.
And then people like it.
One of the last things that is here are some ways to study for things.
Yeah.
I think one important that I learned from lecture is what so I can from working on that course. Yeah. There's so many things that are misunderstood about rectified. Not clear, not yeah. But the rest, yeah, because we got Wi-Fi and yeah. Yeah, on the computer, we replace all the classic computers. They'll let you communicate faster. Yeah, something like that. Yeah. I think you mentioned railroad optical fiber. Yeah. That's one of the things we're studying. In theory, it's possible. The question is, it's in practice because to have as low a box as possible. No amplifiers to allow you. So you have to find an optical path that has no amplifier. Also, no amplifier. But the loss is everything. You happen to have no crosstalk. Like that. Oh, yeah. I had an optical communication person, so O-band and C-band, there's an optical fiber. And one of them's about 100 and like the one's about 1300. Yes, right. And the could have quantum in one band and classical in the other. You can't have quantum in the same band with classical because there's too much.
How about the proximity? Because in one cable there are 69 cores, 69 optical fibers. Is there any risk for crosstalk? That proximity?
I don't know. That's a really good question.
Because there's usually not a single, right?
Yeah.
If one optical fiber, there are more than, for example, 96. Last year I had some practical work, a project in our solar road, and it was the first time one company, solar company, to install. Well, only 30 kilometers. No, I was for classical,
Just be warned, I'm absolutely terrible with that because I get hundreds of email messages and I almost never read my email. So find some way to communicate and keep trying, and eventually I'll answer.
No, but what
Find the consultant.
Yeah. There was a research paper from a group at Oak Ridge National Laboratory. Oak Ridge National Laboratory, which is in Tennessee. Talking about how much compression they need between. And I think they were. Yeah.
Hello, good morning, Prof. Mazumdar. Hello, yeah. Okay, right.
Hello,
Yeah.
hello, yeah.
Just to test your connection, and then
Sure.
we can hear you clearly here. So yeah, welcome. So we just finished our first session with Professor Van Meter.
Okay.
Looking forward to your talk.
Okay.
I'm gonna talk. Yes.
So we'll start in about 10 minutes, Professor.
Sure. I'm fine, but we have I have a meeting this morning. Today
Well, this is a very tightly scheduled trip. You're there. I also have work that needs to be done back in Japan, so it's all kind of complicated. But we managed to get it in for a couple of days at least. So yeah, it's between several different things. Like we had admissions exams on Tuesday, and then there are retirement parties and other meetings and various things that we attend to back at all. So it's all very tight. It's all very tight. I'm going to run to the restroom before we start. I'm going to run to the restroom. I assume there's one nearby somewhere.
Tadi apa? Perlu digas tapi makro. Menarik tentang makro. Kalau digas sebelah mana Pak? Ada ya tulisannya. Ada kok. Ya, bukan ini tadi di posternya Pak. Itu di posternya. Oh. Oke. Ini tadi harusnya jaraknya tuh dari sini ke situ gitu. Gitu. Nah, ini nanti di lab. Nanti kemudian gitu. Jadi yang masuk jadi buat masuk dulu. Oh, kalau sini kok masih banyak Pak. Bukan itu elektro. Oh, Pak. Pak. Kalau kita banyak yang kerja. Mungkin Pak dengar slide. Tadi saya bilang ya kan ada kamera juga, kamera ini juga. Cuma nanti mungkin Pak Adrian bisa jadi kamera yang ini biar kelihatan seperti panggung. Ya, biasanya di yang mana ya? Oh, yang ini tadi Mas. Nanti ya boleh, ntar saya di sini juga. Iya. Oh iya. Hanya di partai politik kita ada Nah, itu tugasnya mengerahkan massa, menghormati pembicara Pak. Nanti dia ngelihat ini acaranya siapa ya? Nasi bungkus ini. Modal nasi bungkus. Tapi yang penting ini, yang penting ada kita di depan. Udah oke. Zoom-nya berapa orang kelihatan nggak ya? Ya, zoom-nya berapa orang kelihatan? Tadi itu beberapa halaman sih. Ya. Soalnya saya dari belakang nggak kelihatan. Oh, dari itu aja deh. Tapi nggak masuk. Banyak ya masuk. Lumayan.
Peserta yang masih di luar, silakan untuk masuk kembali ke ruangan karena acara akan kita mulai. Good afternoon, Professor Anupam Mazumdar.
Yes.
Yeah,
Yeah.
can you
Good
hear
afternoon.
my
Yes.
voice clearly?
Yeah. I can hear you.
Okay, thank you very much. We will shortly begin the session.
Sure. Thanks.
Okay, let's start the session. Now we move on for the second session. We have Professor Anupam Mazumdar, who will share his thought on challenge for creating macroscopic Soniger cat states. We will briefly read his CV. Mr. Anupam Mazumdar is a theoretical physicist specializing in cosmology. He earned his PhD from Imperial College London in 2000 and held research position at ICTP, McGill University, and Nordita. He was a reader at Leicester University and an honorary associate professor at Niels Bohr Institute since 2017. His work includes influential reviews on inflation, reheating, and dark matter, with publication available on Inspire and Google Scholar. Prof. Anupam, the screen is yours. Take your time, please.
All right. So thanks. Thank you very much for your kind introduction, and thanks to all of you for having me now today virtually. So I will be talking about slightly new development in quantum technology, and also asking some of the fundamental questions. And so I came from perhaps from a purely theoretical background, but now I'm mostly working in developing this new quantum technology, which I will share with all of you. So the question is, how would you create macroscopic spatial quantum superposition? So can you imagine that you have a matter or space-time, because space-time and matter, they are related to each other through Einstein's general theory of relativity. So can you construct space-time with matter in two places at once? It's exactly like the Schrodinger cat state. Can you really create a massive Schrodinger cat state with a large spatial superposition? And so this is what I'm going to share with you. And right now we are being funded by Moore Foundations and Sloan Foundations to develop this technology, along with many other colleagues throughout the world. Okay, so so just to very briefly, just to be on this framework. So space-time and gravity is still one of the most fundamental questions in physics, and we still don't understand gravity extremely well, because we understand, for instance, all the interactions like electromagnetic interactions, weak interactions, strong interaction which hold atoms and nucleus. We understand these things, but gravity is still very eluding, despite being a very rich history from 400 years old history from the days of Isaac Newton, Einstein, and many new colleagues. I mean, Feynman and many other colleagues have contributed to this idea. It is still very fascinating, and it's the weakest interactions of all. It has a universality in the sense that it attracts everything, but we still don't understand its quantum behavior. So what is exactly the origin of space-time? And this is what we still don't understand very well. whether it's really a classical system or quantum system. We don't understand. So aim is to understand all these fundamental puzzles and fundamental questions. They are very fundamental in nature in a lab. But often it happens that sometimes fundamental questions pushes the technology far beyond your comfort zone. And you will see today's talk that it is exactly what it does. It pushes the current technological limit beyond what no one has ever achieved on Earth, and something which will happen for the first time ever. If we want to understand this fundamental question, we really have to push our technology. And you see that amazing thing about quantum mechanics or quantum technology is that it is so diverse that sometimes, even the fundamental questions to understand nature of space-time requires disruptive quantum technology. So now here's the plan of my talk. So I will talk a little bit about the foundational aspects, quantum mechanics, macroscopic quantum superposition. Then I will talk about these fundamental implications. You can see that there is a picture of, actually it's an NV-centered nanodiamond. It's a cartoon picture. It's to show that there are two such NV-centered nanodiamonds in a quantum superposition, and they are interacting solely via gravity. Of course, gravity is extremely weak, but we hope that we can perform this kind of experiment in near future. And there are many experimental challenges to overcome. I would say this is one of the a really hard experiment ever would be done. But there are immense applications. So whenever you chase something, a very fundamental question, it also has immense applications. One is electromagnetic levitation, gravitational sensors. These will be the extreme sensors, because if you can measure something very weak, because gravity is extremely weak, then you are creating one of the most sensitive quantum sensor ever on Earth. So let's go back a little bit. So that was the plan of my talk. But today, let's set the stage from something very basic, and let's ask the question which we perhaps all know in the audience, but doesn't help to remind ourselves, what's the difference between classical and quantum mechanics? So here is the Fuld Hall in Princeton, where Albert Einstein is standing. So if you want to understand his classical information, we can actually understand everything. All the compatible properties exist simultaneously. His position, his momentum, his color of hair, or whatever he's wearing, we can find out everything without any difficulty. But in the quantum world, of course, it doesn't happen. In the quantum world, because of the uncertainty principle, you cannot find the spin sigma x and sigma y exactly simultaneously. So because of this inherent uncertainty principle. And this actually gets reflected when you talk about any observations, when you build some correlations. So you can build classical correlations between two systems. You can build quantum correlations between two quantum systems. And it turns out that quantum correlations is much more richer than a classical correlation. So here on your left, there is an example of, say, imagine a spin up and down. And let's say this is a classical spin. So you can build correlation. And rest of the direction, there is no correlations. But in the quantum world, because of the spin itself is in a, it has all the possibilities. There is no preferred direction. So you can build correlation in X direction, Y direction, and Z direction between the two quantum systems. So, and from quantum systems, you can also build classical correlations. So you can, I have shown the state of 0, 0, and 1, 1. So 0 and 1, these are two quantum systems where I can build classical correlation, and I can build much richer quantum correlation. And the example in the B is a perfect example of your entangled state. So entanglement is one way to extract this quantum correlation, which is bona fide. There's no classical analog to this property. It's inherently quantum. So quantum mechanics presents much richer observations, much richer correlations between two quantum systems. And coming back to entanglement, so we all know that in a quantum system, whenever you have an interaction, your system gets entangled. So what entangled means is that your states cannot be separable. And the right-hand side of the example is your example of an entangled state. on the left-hand side, where you can separate the two states of A and B. That's the product state. That's your separable state. It's an unentangled state. So as I said before, and we all know, that entanglement is a bona fide quantum entity, and it has no classical analog. So it's a very interesting way to demarcate between classical world and quantum world. So what is exactly this protocol? So the protocol is, the quantum protocol is based on something called LOCC. And LOCC and its counterpart is LOQC. So it's actually a very well-known protocol. It has been known for almost 20 years, or more than that, given by Bennett and company, and many other colleagues have contributed to this. So the idea is very simple. So you have got Alice and Bob, two quantum systems, and they're separated from each other. And imagine that if Alice and Bob, they're interacting or they are communicating purely via classical channel. And if they were to do this interaction or communication purely via classical channel, they were not going to get entangled. So A and B would be separable or separate states. So that's the statement of local operation and classical communication. So local operation and classical communication cannot entangle any two quantum systems at all. So in order to entangle this Alice and Bob's setup, you need a quantum communication or quantum interaction between Alice and Bob. So you need to set up quantum interaction. And if you can do that, then you will see that Alice and Bob can get entangled. So there is no entanglement via classical mediation or classical mediator, but via quantum mediator, you can get an entanglement. And this is the essence of this experiment, which we are pursuing right now. So, of course, I don't want to get into the details of what's called quantum and gravity. If you don't have to understand anything about it, just one slide is sufficient. What is the definition of quantum and gravity, or the space-time being gravity? Is that gravity being space-time being quantum? Is that its ability to perform quantum communication between two distant space-time regions, hence generating quantum entanglement between the quantum systems. So this is just the most basic definition which you can ever imagine in quantum gravity. And that's all we need. We don't need anything beyond that. So this is the layout of the experiment. So the layout of the experiment is that the claim is that you can test the quantum nature of gravity. So you create two quantum systems. These are matter wave interferometers. They're separated by a conductor. It is extremely good superconductor because you want to mitigate your electromagnetic interaction between Alice and Bob. You will let only the gravitational interaction mediate between Alice and Bob. Imagine you have spin which is embedded in the system, and you have created a macroscopic Schrodinger cat state for Alice and for Bob. You keep the system alive for some time, say t. And at the end of the experiment, what you measure is the spin. How many times you have got spin up between the Alice and Bob, or how many times you are getting spin down and spin up and spin down. And between the spins, you are building correlations. And the entanglement is due to gravity. Gravity cares about the mass. So this entanglement also gets reflected in your spin, which is embedded in the system in the center of mass. And that certifies if you get a spin correlation, if that correlation tells you it's like entanglement, that's the one few minutes ago as we spoke about. If it shows that entanglement between the two systems, you can certify the space-time is quantum. So this is the protocol, and you require something like nanoparticle separation of 10 micron superposition, and you immediately see that these are extremely, extremely challenging experiment. So far, no one has ever done before. Now, for any entanglement, so how do you witness entanglement? So for a bipatriarch system, so you have got spin system, let's say spin up and spin down, and you have got two systems. There are many ways you can do entanglement witness. You can do a classic way, perhaps through Bell's inequality test you can do, but there are much more sophisticated witness people have constructed. There's a huge literature about constructing such witnesses. in a review article by Horodecki and Horodecki. But a very simple witness which you can construct is called, is given here, the equation, this W, which is taking the correlation between the Pauli matrices of system 1 and system 2, sigma x1, sigma x2, sigma y1, sigma z2. So these correlations are in complementary basis. And if the trace of W times the density matrix rho, if it's less than 0, you can say that you have detected entangled state or entanglement. So what happens here? So the argument is very similar to electromagnetic system. So suppose if you have got two charges, you know the electrons, quantum is inherently quantum system. If you place it in an electromagnetic wave, then you can ask a very simple question. The moment I put two charges, they will start either repelling or attracting depending on the nature of the charge. So, and how it is happening? It's happening through the intermediate interaction between the photon and the electrons. Something similar happens in the case of gravity. So if space-time is inherently quantum, well, in the case of photons, you know, photon is quantum, electrons are quantum. So you know that already. But in the case of gravity, we don't know. So if space-time is quantum, then the change in the gravitational energy due to the two quantum, let's say quantum harmonic oscillators, will also give rise to change. The change in the energy will also be quantum. So what it means is that the simple Newtonian potential, which everyone sees even at the childhood days, in every school, perhaps is being taught. Now that in a quantum world will be an operator. It will not be a C number. It will not be a complex number, but it will be an operator acting on some Hilbert space. And you can actually write it down. Order by order, you can write it down, all the terms, and this is something which people write it. Especially this is very common when people talk about the coalescence of this LIGO events in gravitational wave astronomy. The two black holes come and interact with each other. So this is what happens even for gravity. And now how do you do the experiment? So the experiment, I have shown the picture. So what you do is that you create a superposition, which is system 1, a spatial superposition, macroscopic superposition, and then system 2, and you are building the spin correlation. And one of the important criteria is the order parameter. What is that order parameter you are looking for? So what you're looking for is the entanglement phase due to the gravitational exchange. And this entanglement phase is given by this quantity gm squared divided by h bar d times the tau, the time your experiment is alive, and the superposition size delta x, and d is the separation between the two center of mass. Yeah. Now you see that G is a very small number, actually. The Newton's constant itself is a very small number. H bar, the Planck's constant, is extremely small number, but the ratio is not. And there is a Goldilocks zone where if you can tap it, then you can get the entanglement between the two systems purely through gravitational interaction can be made order 1. So what are these order parameters? So mass is roughly order 10 raised to minus 14 kilogram. If you create a superposition of 100 micron, D is roughly 500 micron, tau is roughly 1 second, then you can get entanglement phase, which is roughly order 1. Now, this is exactly the picture which actually our IBM, Google, or any ion-based quantum computing setups are performing, except that instead of gravity, you have a photon mediation and you have an ion. For ions, you don't require large superposition. The Gaussian superposition is sufficient. You don't have to keep the system alive for 1 second. You can keep the system alive for microseconds or milliseconds, and you can still get enough large entanglement just via Coulomb interaction. So this is a very similar protocol. Essentially, if you want to call it, you can call it a gravitational quantum computer. But as we know, with any quantum system, it is extremely, extremely hard to maintain, to create such a superposition, because you're doing this experiment in an environment, and in an environment, there are unpredictable noise, fluctuations. Everything will destroy this coherence of the system, of the matter wave interferometer. So as a consequence, which we call it like decoherence, in the quantum system, in the quantum world, we call it a decoherence. And because of the decoherence, your of diagonal terms in your density matrix will gradually go to zero, and you are left with only the diagonal elements. And so this decoherence is one of our biggest challenge, how to control the decoherence of a system, how to maintain the coherence of the system as much as possible, how to create the pure state as much as possible. And this is where the quantum technology and quantum challenge ups the game beyond what people have achieved so far. So the experiment depends crucially on this the witness, because this is what you're looking for. It depends on your decoherence rate gamma. Gamma is your decoherence rate, the entanglement phase, which I had shown you before. So this entanglement phase, this delta phi entanglement comes in, and in order for witnessing any entanglement, or in order to see the entanglement is building up, you require this entity, so 2 gamma t minus delta phi entanglement has to be less than 0. And you can see that for a 2-qubit system in a various setups, so for different masses, you can see depending on your decoherence rate, the witness changes, witness becomes different. So you see that depending on how good the witness can be, or how well can you read the witness from the system, how well can you read the spins of your macroscopic system. Based on that, the mass, the superposition size, the witness, and the decoherence rate changes. So this is an example. On your right hand side, you see this delta x is the superposition size. So if you can witness a very small number, then even a 1 micron superposition size for 10 raised to minus 14 kilogram is sufficient, provided the decoherence rate is roughly around 10 raised to minus 3. So, but getting the decoherence rate 1 part in 10 raised to 3 is extremely, extremely hard, as you will see in the next couple of slides. So why? Because also it depends, when you do this kind of experiment, the decoherence rate also punishes you. If the decoherence is very, very large, let's say gamma is 0.1, let's say, just to give an example, you need to repeat the experiment. For 2-qubit system, as I mentioned, you need to repeat this experiment many times to get large confidence level. But if the decoherence rate is small, if you can control the decoherence rate, then you don't need very many repetitions. You can do with very few repetitions, maybe 100 repetitions, you can certify with a large confidence level that you have seen the witness or the entanglement. And based on that, the requirement of coherence or managing the decoherence leads to extreme conditions. So just to give an example, if you want to have a 0.01 hertz, so here the gamma is the decoherence rate, and if you want to create a superposition size even up to the order of, say, picometers, say 10 picometer, you require a temperature of around 1 millikelvin. And the gas pressure has to be very, very tiny, 10 raised to 10 per meter cube. The pressure has to be, of the surrounding pressure, has to be around 10 raised to minus 16 Pascal. So these kind of experiments require extreme protection, because you want to create the system as pure as possible, from quantum mechanical point of view. And if you want to go for larger and larger superposition, let's say 10 micron superposition, then the number in the container, in the particle density has to be even lower, something like 10 raised to 9 per meter cube. And the pressure has to be something like 10 raised to minus 15, 10 raised to minus 14 Pascal, but the temperature has to be around below Kelvin. So we are talking about something like cryogenic environment. So in a cryogenic environment, you really need to place this experiment and perform the experiment in a very, very good ultra high vacuum. So now, so the challenge now in this context is how well can you maintain the quantum coherence? So the first thing is you have to obtain something called you have to control the motion. So you have to create a vacuum. You have to create a potential, well, in some sense, where you can trap your particle. And not only you can trap it, but you have to make sure that its motional ground state is achieved. Because if the particle is jittering, then it's very hard to create this macroscopic superposition, or it's even very hard to create any superposition, as a matter of fact, because you don't know. So you need to know the position of a particle extremely well. But particle is not a point particle. It's a rigid body. in some sense. Let's say it's an envy-centered diamond, nanodiamond. It's a rigid body, so it has all the Euler angles, alpha, beta, gamma. And you need to make sure that not only your position and momentum gets under control, but you have to make sure that the particle is not librating, it's not moving like this. You have to control its all the three Euler angles, alpha, beta, and gamma. You have to place such a system in an extremely high vacuum, as we discussed, and to protect the system. And you need to protect the system from electromagnetically, because you don't want any electromagnetic interference in your system, which will dephase the system. And then you need a very good vibrational chamber. So you have to protect, you have to keep the system with the with the help of oscillators, inverted harmonic oscillators, and you have to get one of the best vibrational chamber where you can perform the experiment. And so the experiment requires, it's all about noise, because everything is about noise. So there is a whole list of understanding the noise. I have just presented you very few numbers, because this list goes on. It is an unending list. Everything causes trouble, so everything is noise. So here, for instance, for creating, say, 10 femtometer superposition, you need to control the decoherence rate, or time, or the time of the experiment has to be something like 10 microsecond. The pressure is 10⁻⁵ Pascal. The acceleration noise is roughly 10⁻⁴ meter per second square per square root of hertz. The current noise, because after all, everything is happening through current, I will show you, the current noise has to be ampere per square root of hertz. Because of the current you are creating magnetic field, the gradient in the magnetic field, which is eta, that has to be something like 10⁴ Tesla per meter per square root of hertz. So these noises you need to compute, and you need to compute these kind of noise for various superposition for mass, say 10⁻⁻14 kilogram. So you need, it tells you that you need extreme protection, extreme isolation environment to perform this kind of quantum experiments. Now, why levitation? So levitation, now we are moving towards more and more quantum domain. So the levitation, why we need levitation to build this kind of Schrodinger cat state of nanoparticle, because it's not clamped. In a clamped system, you cannot create, you really need to control even more. But the levitation has its own advantage. There is no contact, though there is no physical contact. You are actually levitating the particle purely through electromagnetic interaction. Extremely high Q factor. You can perform the experiment in a very good vacuum. You get long coherence scale, and you can create exotic quantum states. And this is what we want to create. We want to create extremely exotic, non-Gaussian quantum states. So this is an example, a picture from one of my collaborators. So my partners are from UCL, Northwestern, from Yale and Warwick. And then we have other partners from Austria and also Israel. So we worked, quite a lot of partners, but these are the core partners for this particular experiment where we are trying to levitate it. So this is an example. In the middle, you will see that there is a small shiny object that's actually envy-centered and nanodiamond, which is being levitated in a real experiment with the help of fixed magnet. And the width of the magnet is roughly 3 millimeter. But now what we want to do is that we want to miniaturize everything in a small chip. The chip is roughly millimeter size chip, in like an atom chip. So this is the technology we want to go for, and this is what we will talk about for the remaining time. So why envy-centered? Because you need to host the qubit. So you need to play with the qubit, because it will become clear why we require a spin, because spin can interact with the magnetic field, and in an inhomogeneous magnetic field you can actually create a spin. You can split the spin, like your Stern-Gerlach experiment, the famous Otto Stern and Gerlach's experiment, which is roughly 102, 103 years old. This old technology is still now you want to capture, but you want to capture it in a very tiny chip. So that's why we require a spin or a system or a material which can host a qubit. And NV-Center provides that simple example. First of all, it has a We understand the spectroscopy very well. We can do optically, we can detect the magnetic resonance of various states of ground state and excited state for the NV center. Especially people like to play with NV minus. So NV minus stand for so two spins up and down. So this is your both the spin is down, this NV minus, NV plus, and this NV0 state. So these are the three possible configurations you can construct in the nitrogen vacancy center. So the idea is that you can actually manufacture this kind of, in our lab, especially in Gavin Morley's lab, he produces one of the best NV center nanodiamond. So what do I mean by the best? You need to get rid of the impurities, because the carbon is not completely carbon. You may get some carbon-13 or carbon other carbon isotopes you may get. You need to get rid of those carbon-13. So you require the carbon-13 population to be very, very tiny, 1 part in per billion, actually. So that kind of purity you are talking about. You have the vacancy where you can embed the electron. You can do that even from outside, either through laser or through laser implantation. You can place this, first of all, you can also create a vacancy very, very close to where you like. You can go very deep also, deep inside the diamond. Again, through laser implantation, you can actually implant electronic system there, and that electronic system becomes your, effectively plays like your qubit. So some of these things are feasible right now with our technology, and you can measure the coherence time in room temperature as well as in cryogenic temperatures. So one of the best record is held by Gavin Morley's group in Warwick, where he can get the coherence time scale. T1 roughly around milliseconds, and T2 is roughly around 780 microseconds. So these are the achievements of our group. But there are other techniques which actually you can employ, where you can make the coherence even beyond minutes. And that technology comes essentially from our neighboring institute, University of Delft. So there is a group by Taminiao group where you can actually map the electronic spin. So you can take this electronic spin, you can map it to nearby nuclear spin, and hold the information of the electronic spin for a much longer time scale, roughly around a second or beyond second. Or you can do dynamical decoupling or mapping of the nuclear spin. Both the ways you can enhance the electronic spin of NV for a much longer time period. So all these techniques we are using to actually create a very long coherent system for our experiment, but there are other alternatives. It's not just limited to NV-centered. We are also looking for doping, say ytterbium ion or rubidium, some kind of like in your system, such as noble solids like xenon or even helium. You can actually embed, you can implant, you can dope the Rydberg atoms. So these are Rydberg atoms, which is now very useful, especially after last couple of years, where people are using it in quantum computing systems. You can use the same thing. You can take a Rydberg atom and implant it in some noble solids, and maybe you can remove the it depends on how well you are creating these noble solids, because you don't want any imperfection. While creating itself, you may create imperfection. So you need to be very careful in creating these noble solids such that there is no defects, there is no imperfections, there are no stray bonds and things like that. And even for NV-centered nanodiamond, we need to clean. We need to clean the surface extremely well, because if you just take NV-centered nanodiamond, you play with it in your experiment, it starts burning. Why it starts burning? Because there are too many impurities, and the impurities absorbs the photon, and that heats up your nanodiamond, and it doesn't really work very well. So you need to make a very pure system. You need to get rid of the dangling bonds on the surface. It's all about understanding the material aspects of your NV-centered nanodiamond. You may have to coat it, maybe with some material where you or some conducting coating, which will get rid of the stray bonds or stray spins on the surface of the NV diamond. So you need to do quite a lot of material engineering to get rid of the impurities of the system, to maybe some hybrid system where you have where NV-centered is embedded in other material. So you need to come up with all these kind of possibilities to make the system as pure as possible.
For interval, you have 10 minutes more. for
Sure,
contributing.
thanks. Thank you. So, so the idea is here is that you're really taking this nanoparticle and you're levitating on a chip. So on your middle, you see that there is a small dot, which is actually being levitated on a chip. So, and the chip you are creating with the various wires, and I will give you some of the parameters of the chip which we are creating. This is a very high-end chip. Such chips are not created in any labs. So we are creating the chips in Chicago right now. And this is the configuration of the chip where you are levitating a nano diamond. So this is a rough configuration of the wirings, the Z wiring. And this is being levitated purely diamagnetically. So diamagnetically means that because the diamond is diamagnetic material, and as the current is flowing, it's creating a magnetic field, and it's levitating your nano diamond on top of the chip where we are going to perform the experiment. So there are two potential wells, one to control. So narrow potential well, you can see for cooling. You want to cool the nano diamond, motional cooling, the ground state cooling, and a long trap where you want to create a macroscopic quantum superposition. So the diamond can move in that long trap. At any point in your experiment, you cannot touch the diamond. It has to be levitated always. So that you are creating a lift, and the lift is through diamagnetic levitation. So you want to take the nano diamond physically from point A to point B. You don't touch it. You do it through your diamagnetic levitations. So everything has to be done through diamagnetic levitation. And as you can see that because envy-centered diamond now has two spin state up and down, you can actually, if you let the inhomogeneous or magnetic field. So here is an example. It's a cartoon picture of an inhomogeneous magnetic field. If you create a gradient in the magnetic field, then you split the two spin states. And as you split the two spin states, there are two forces for the two kinds of potential you obtain for a spin up and spin down, and that creates a tiny superposition. So here, this is an example of a 10 raised to minus 17 kilogram nano diamond, and you are creating a spin up and spin down, two different states. So this is your example of your Schrodinger cat. Usually people show very fluffy cats when they want to show Schrodinger cat state, but here, this is a simulation of a Schrodinger cat state where you can see really the superposition occurring at roughly around, this is a very tiny superposition, but still it's extremely hard to achieve it in real life. It's around a micron size superposition you are creating here for 10 raised to minus 17 kilogram, but you can see how the spin up and spin down trajectories are going to behave. So these are the things which we are doing in our lab, and we now want to perform this experiment on a chip. And there are various schemes which you can employ to get even a superposition size even larger, something like 40, 50 micron, or even close to 100 microns even, by using various chip designs. So chip design and the superposition go hand in hand, because it's all about playing with the magnetic field. So you can trap it in a harmonic potential. You can create an inverted harmonic potential where you can let the system flow, the two spin up and spin down system, and enhance the superposition because of this instability which you are creating in the magnetic field. So all these stages here on your left-hand side, you see T1, T2, T3, T4, T5, they are now embedded on your chip. And the chip is creating, you're switching on and off. These are very efficient. And as you're switching on and off, you are creating different magnetic field profile. And as you're creating different magnetic field profile, you're creating different superposition schemes. But the question is, how well can you control the current, for instance? So the current fluctuation or the magnetic field gradient fluctuations has to be very, very tiny. So these are the milestones which we need to achieve before we perform this kind of experiment. We need to test all these parameters in our lab. And so prototype experiment has been done. So prototype experiment has been done with the help of rubidium atom, with our collaborators from Germany, Israel, and UK, and Netherlands. So with 10 raised to minus 26 kilogram rubidium atoms. So in a Stern galaxy, so exactly the same thing which I have mentioned here in this plot, the same thing you can do with the help of rubidium atoms. And the rubidium atoms you can split. The two spin systems, you can split it and create a superposition with the atom, it's the atom interferometer on a chip. So this experiment has been done on a chip but with the help of atoms. And you have created a superposition, a tiny superposition for a few micron, and you can keep the system alive. But now we want to up the game from 10 raised to minus 26 kilogram. We want to make it to 10 raised to minus 14, 10 raised to minus 15 kilogram. So really macroscopic system. So in the remaining 5 minutes, I will talk about something which actually involves one of the students from your country, from Indonesia. One of my students is the first author, Rizaldi. He comes from Indonesia. And recently we have published something very interesting paper. It's about, as I mentioned a couple of minutes ago, that your nanodiamond is not a point particle. It is a rigid body. It has its rotation. So when you talk about this matter wave interferometer, you have to make sure that not only your position matches, your momentum matches, but all your internal degrees, these angles, the Euler angles, alpha, beta, gamma, they will also have a quantum evolution. They have to match as well to get a large contrast. And some of these experiments, so essentially these experiments, classical experiments, people have done it. It's called Einstein-de Haas effect. People have seen the rotational effect. So you let the nanodiamond in your vacuum, it starts rotating. It starts rotating because it has the NV centered, which is off-centered from the center of mass. In presence of magnetic field, it exerts a torque, and that torque leads to rotation. But now you need to control that torque. You need to control that rotational parameter. So these are the extreme maneuvering of your quantum system based on your NV spins. You need to understand and you need to employ in a real experiment. So as I said, that there's the spin. Otherwise, what will happen is that when you do the experiment, when you end the experiment, you will see nothing. So you have to have a very, very good contrast. And in order to contrast, you have to make sure all these parameters. So if you do perform the experiment in one dimension, your momentum in one dimension, your position in one dimension, the wave packet of the two quantum systems, as well as the Euler angles, they should match so that you can get a large contrast. And so one way you can obtain it if you impart a rotation. So what we are trying to do is that now imagine you have a nanodiamond which we can etch it like in cylinder, and you can rotate the cylinder. So it's like a bullet. So when you shoot a bullet, what happens? The bullet rotates and goes. So exactly, you are now creating a superposition where up and down states of your bullets. So two bullets now in the left arm and right arm, they're rotating very fast, and then they are matching to get a large contrast. So some of these things now we are trying to employ it in even at the classical level. We want to control this rotation at the classical level for a nanodiamond, again in a levitated setup, levitated vacuum, which we talked about extremely, extremely well. And these are the simulations for this NV spin up and spin down, because you're creating superposition for spin up and spin down states, and you want to understand how the libration mode is evolving, how the fluctuation in the libration mode is evolving in presence of the inhomogeneous magnetic field as you are performing the experiment. So these are the examples of 10 raised to minus 17 kilogram for spin up and spin down, and you want to create a Schrodinger cat state, but you want to understand how these libration modes behave. And as I said, so this is one libration mode. So this beta angle is, suppose this is your NV and this is your NV axis, and you are employing a magnetic field in this direction. But there is some small uncertainty. You would like to give a magnetic field along the NV axis, but it can never happen. It will never happen. So there will be some tiny fluctuation. So you want to control that tiny fluctuation extremely well. So that's the essence. And as you're controlling the tiny fluctuation between the magnetic field direction and the NV axis, you're controlling one parameter, which is beta, and also you're controlling other two Euler angles, alpha and gamma. So you also have to understand how the alpha vacuum, how the alpha, the state, and the gamma evolve in time in presence of this quantum potential and its fluctuations. So you need to mismatch, you need to understand this mismatch, and based on that, you can look into contrast of the system. So this tells you how much rotation you need to impart in your system. So maybe 20 kilohertz, 80 kilohertz, depending on temperature corrections as well, because these are the internal temperature. You're not talking about the external temperature, you're talking about the internal temperature of the phonons, because the spin also talks to the phonons. So all these are about understanding the quantum system extremely, extremely well when it becomes macroscopic. So one of the application which will be future application for all of us will be to understand in quantum sensor, because these are extremely sensitive quantum sensor you are building. You can employ it in your space to monitor space debris. So this is something which people are talking about with various space aerospace companies, which we are also talking about, discussing these future prospects. So you can detect space debris 10 meters away, kilometers away with certain velocity. You can do a tomography and you can actually warn your system much before the impact happens. So B naught is your impact parameter, V is the velocity of the debris, and local acceleration. So your matter wave interferometer can sense the local acceleration. It can sense 10 to minus 20 meter per second square. You see such a sensitive, acceleration, very tiny acceleration, which your matter wave interferometer can actually sense it. Far away, from 10 meters away, it can sense it. You can employ this in your earthquake zones, tsunami zones. So these can be adopted as early warning systems in future. So these are extreme quantum sensors which you can build and you can deploy it in space and elsewhere. And you can know about which angle, from where it's coming, the disturbance is happening, all these things you can try to understand. You can ask various fundamental questions, of course, about nature of gravity, nature of physics beyond the standard model. I will not get into the details of this unless someone is interested. You can actually probe physics beyond the scale of LHC today. LHC, is a famous experiment where they have seen the Higgs potential or Higgs field, discovery of the Higgs field in Geneva, which has its limitation. It can go up to 10 to 4 GeV, but these experiments can probe physics even beyond 10 to 7 GeVs. So there are many advantages of future employment of this quantum technology, harnessing this quantum power in various fundamental directions. You can even detect dark matter. So people are employing, detecting dark matter such as axions, and there are many experiments throughout the world, actually, in China, in Japan, in America, in Europe, everywhere such experiments are doing. But now with this entanglement protocol, because now if you can entangle things with gravity, you can entangle via dark matter to systems. You can actually probe the white region, which is much beyond, much smaller in strength, much smaller in mass. So you can detect mass of 10 to minus 30 electron volt, which is a very, very tiny, small mass. So, so you see that, it's amazing thing that the simple understanding fundamental questions actually helps the technology. It touches upon many different aspects of physics. It touches particle physics, it touches condensed matter, it touches the material science, it touches upon the laser. I didn't get the time to talk about the laser physics. It touches even astrophysics, cosmic. You need to protect it from cosmic ray background. So effectively, it essentially touches upon every branch of physics you can ever imagine, just to understand this, understand the nature of quantum, nature of space-time. And the research topic has been now it's being highlighted in many places, including Nature and others. So it's really a community effort. We are trying to build a community. It cannot be done in one lab. The kind of facility we are talking about, we require international cooperation. We are talking with various different countries, from Japan, from within Europe and America, and Canada as well. So because you need to develop many small things, from material science to understanding the interrogation of your NV center. I have only spoken about through optics, but in future we will not interrogate your NV with optics, because that's useless. It'll heat up my system. Optics is a useless thing to do now. Now we will employ quantum non-demolition tests. Completely different kind of sophisticated test to read out the spin of your NV center now. So all these things have to be developed, and gradually we are inching towards that. Now, it always reminds me, when I was a kid, I would watch this Star Trek, where the Captain Kirk would tell me, beam me up, Scotty. Captain Kirk would be 60 or 70 kilogram object. And here we are now struggling to create such a superposition or teleportation, if you like, of 10 to minus 14 kilogram, even for few microns. So this is the dream. Hopefully we can achieve it in a community. And this is the program which we are aiming for. Of course, we want to understand whether the nature of space-time, but it also opens up a door for creating exotic quantum states such as macroscopic superposition. And we want to go for the superposition from what we have today all the way to, say, 10 to 100 micron with the coherence of 0.1 to 1 second. And in this journey, we are hopefully proving new physics, fundamental physics, but also huge amount of applications. And so thanks a lot for your attention, and thanks for your listening. Thanks. Thank you very much.
Thank you very much, Professor Anupam, for your insightful presentation. Now we move on for the question and answer session for this time. Is there any question in the room or in the Zoom meeting room? We open for 2 questions. Okay, from Prof. Adrian, please have the mic.
Hello.
Hello. Yeah. Thanks. Yeah.
Again, yeah. Very interesting presentation, and also interesting topic. I know little about this topic. So if I can summarize correct. I don't know if it's correct or not. You want to prove the quantum gravity, yeah, I think. And normally, if I want to show that there is a phenomena for quantum gravity, we go to a massive object like black hole and observe quantum phenomena over there, possibly observing the Hawking radiation or something like that. But now you go to a very small object, very small mass, and this is very interesting. Then what I want to ask is, we have LIGO, right? LIGO gravitational wave detector. And your presentation, from your presentation, now we can conclude that what they detect is gravitational wave, but not graviton. Is that right?
Exactly. So the LIGO experiment can probe the gravitational waves, but not the quantum nature of this graviton. And to probe this quantum nature of graviton, we need to create this superposition. So yes, so we are not going for very heavy, massive systems. We are going for small systems, but we have opened up the completely quantum domain through the macroscopic Schrodinger cat state. And the trade-off is creating now superposition. If I can create a large superposition, so tomorrow, let's say 100 years from now, people can create a 1 meter superposition for such massive objects. People do create superposition. Atom interferometers are creating 0.5 meter superposition, but with the atomic mass, 10 raised to minus 24 kilogram. But now imagine if you can create for 10 raised to minus 14 kilogram, 0.5 meter superposition or 1 meter superposition, then you can do not only fundamental tests, but also it has its own, because these are even more sensitive than atom. The sensitivity comes because the mass, you make the mass heavy, so even a tiny fluctuation it can measure through the phase. And so you open up a completely new domain in physics or in technology that you can probe very sensitive things, very sensitive interactions and unknown interactions, or small tiny vibrations, you can probe it. So it opens up a completely new chapter for for humanity, I would say.
Yeah, thank you. Second statement, so I want your comments. So in this experiment, you are not going to detect the graviton directly, but only observing the entanglement.
Yes.
And then you conclude that, okay, there is graviton up there. Is that right?
Yes, that's true. You never probe things directly. You always probe things indirectly. Even in the LHC, when we are probing Higgs, we never see Higgs bosons. It decays immediately. So you probe it the internally, the Higgs exchange. So here also we are inferring the graviton exchange. So the exchange is whether the exchange of graviton is classical or quantum. You can probe it.
Any other questions for the last one? Okay, from the audience. Hi, Professor.
I'd like to ask about, you said about the IC design using based on what? Based on quantum. And then you mentioned about it depends on the little current and what spin and also the angle. Oh, what is that? And then how this chip can be done and what is the effect of the future IC design then? Thank you.
Yeah, so it's a very good question. So the idea is that you see that you are creating this kind of chip. First, you as I said that the idea is that you control the motion of your system, of a macroscopic system, on top of the chip. So the chip is being levied. So imagine you have a chip, which is you see it's a millimeter size. So 5 millimeter by 5 millimeter. The current thickness is current is flowing around 12 amps, 30 micron chips. In between the two layers, there is a superconducting. So you're performing this everything in a superconducting setup. So the superconducting sheet is your niobium, which is one of the best, which can withstand large magnetic field. This is a type 2 superconductor, and but you have to control your current as well as your magnetic field. Magnetic field cannot be above 0.9 Tesla because then it will spoil the superconductivity. And in this setup, you are trying to first hold the macroscopic system. You want to control the quantum system, you want to get it to the quantum ground state. And the quantum ground state has been achieved, but it has been achieved optically. In the group of Vienna, people have achieved quantum ground state of a massive object. Even LIGO experiment has achieved for 10 kilogram mirror. They have actually come very close to the quantum ground state. But what it means is that you are controlling the motion of a particle. But the particle can itself heat up. So whenever you try to make sure that your motion is under control, but the bulk of the material gets heat up. That's the problem. That's one of the problems. But you don't want to heat up that bulk of the material because you can start exciting the phonons. If the phonons get excited, then it's not very good for the experiment because the system is internally hot. So you have to make sure that not only you can control the motion of a particle, but also the internal temperature of the particle is small, something like below 4 Kelvin. Why? Because if you have a very high temperature inside the system, then it will interfere with your NV spin. Your NV spin will start jittering. So you want to control not the NV spin, but what I'm saying is that there will be internal degrees of freedom which will interfere with this NV spin as well through kinetic motion. And you don't want to make it happen. You want to control that as well. So you want to make sure that internal temperature is small, external temperature is small, and the particle motion is under control. And you also want to make sure that all the rigid body, there is no, initially to start with, there is no rotation. If you want to give a rotation, you want to give a very controlled rotation. So you know exactly how the states are changing, how the states are behaving. So it requires extreme quantum manipulation of your system. So this is what we are now trying to demonstrate. Maybe in the next 5 years, 10 years, this is what we would like to demonstrate. Once we demonstrate, then you can see small superposition happening, and then gradually from small to large and whatever you want. Once we understand this technology well enough, then you can really open up a new domain altogether. I hope it answers your question.
Thank you very much for the question. I'm sorry to say this is the end of the session because we have a limited time, but it is very interesting discussion because we can continue on the next event. As we come to the end of today's event, I'd like to take a moment to reflect on what we've learned. Quantum technology is no longer just a theoretical concept. It's becoming a reality that will shape the future and of countless industries, from healthcare to finance to cybersecurity. Thank you to all speakers, Prof. Rodney and Prof. Anupam, for joining us today, and for all the participants here and in Zoom meeting. Thank you very much for joining us, and the organizing committee for making STEI ITB Quantum Day 2025 being success today. Let's continue to explore, innovate, and collaborate as we move forward in this exciting field. On behalf of the organizing committee, I wish all you a wonderful today. Stay curious, stay inspired, and let's keep pushing the boundaries of what's possible. Thank you very much for joining us. Thank you and good day. Assalamualaikum warahmatullahi wabarakatuh.